not covered in first, which were not covered. Okay, so yesterday I stopped at the 0.6, now 0.7, or I think in my original plan it was 4.8. What's about some generalizations?
Generalization or Penlevé here?
Penlevé was 6. And it appeared yesterday. But in principle, I can embed Penlevé and also at 8. Let me recall at least something which was yesterday. Yesterday we have a relation. We consider only one example of cassette construction. We have affine SL2 of the level k plus 1 of the level k plus SL2 of the level 1. This is a rational algebra, very simple. For example, we do not see its counterpart in the we take a limit of conformal block above. And this is more or less equal to the sum of SL2 of the level k plus Virasoro with b squared equal to minus k plus 2 over k plus 3. And here on the left side we have just the sum of the algebras, or better to say tensor product of the vertex algebras, and on the right side we have not just product of the vertex algebras but extended. This is what I try to call coupling of the vertex algebras, but there's no Vanya Loisov, so he didn't ask me what is the definition, but I don't have any good precise definition. At least in this case it's clear. I said what we have on the right side.
Should be k minus 1
or k plus 1 on the right side. Something should be correct. Okay. In terms of Nekrasov parameters, what we have here, say, epsilon d epsilon 2. No, better maybe here we have epsilon 1, epsilon 2. Here. Yesterday, instead of epsilon 2, I wrote 2 epsilon 2 everywhere in order to stress this construction as an invariant part of the modular space. Today, I, for simplicity, ignore these two. Maybe I should recall formula for the level. If I didn't make mistake, you maybe result of here. This formula should agree with the following idea, that if the limit epsilon 1 or epsilon 2 goes to 0 should correspond to classical and critical limit of the level, and also here the levels here and here should differ by 1. This is a way to check it, I hope. Okay. This was yesterday. Now let's discuss what can we do with this. as some sort of motivation, I should say that I explained that, at least I said, that the relation conformal blocks for these algebras is equivalent to some sort of blow-up relation, Nakajima-Yoshioka blow-up relation, but with insertion of surface defect. So on the right side, we have functions of two types: conformal blocks for affine SL2 and conformal blocks for Virasoro. Partition functions for pure gauge theory and gauge theory with defect. One can ask what happens for if we do not have such defect. If we have just honest Nekrasov partition function relation, honest Nekrasov partition functions.
And what does it mean that something is happening with instant on some life? What is happening? It depends.
If I want to have this, then I want to have a relation of this type, but now for Virasoro algebras. Have two Virasoro algebras, and again with the same epsilon parameters. These parameters can be read of the blow-up. Now, again, if we again look to the blow-up formula, we know that on the left side we also should have Virasoro algebra with parameters epsilon 1 and epsilon 2. The natural question is how to get this relation. And in this case, the construction is known, and it goes by Drinfeld-Sokolov reduction. Quantum Drinfeld-Sokolov reduction. This reduction, what it means that we have affine SL2 with currents E of Z, F of Z, H of Z, and you add also fermions, psi and psi star. And then you define a differential Q, which is, okay, I forgot to write maybe I write wrong formula, but I hope I will be correct. So first we can define the current probably. Q of Z is equal to and then define differential So in which space it acts? One can take the vacuum module of the SL2, so let me say that here's a level K, multiply by standard representation of the Clifford algebra, psi star. And on this space, we have action of the Q. This space is itself is a vertex algebra, just product of vertex algebras, and one can compute cohomology of Q, and it's easy to see that the cohomology will be also vertex algebra. And the statement is if you start from the SL2 of the level k, then in this case you will get Virasoro algebra with a parameter b squared equal to minus 1 over k vector. So if k is integer, then this parameter for coset corresponds to unitary minimal models, and this is not minimal model, not honest minimal model. Just it can be something logarithmic, but for integer positive key. What I'm trying to say is that one can do the same here. So one can take this coset decomposition and apply Drinfeld-Sokolov reduction. The only question, maybe the first question, it's which SL2 use, from which SL2 we should use for this. Of course, if you want to have on the right side sum of two Virasoro algebras, it is natural to take the diagonal SL2, which have level k plus 1. So if we apply the Drinfeld-Sokolov reduction to the SL2, the level k plus 1, what we get? We get on the right side, we get Virasoro with parameter k plus, so we get two Virasoro algebras. One of them will be with parameters, another One can ask what happens with epsilon parameters which I use, and the answer is nothing happens. They remain the same. One can, for example, what can be seen here? That here we have b parameters, say b1 and b2, and they satisfy a relation. b1 squared plus b2 squared is equal to minus 1. Let me recall that if I relate this b parameter for Virasoro to epsilon parameters, so the standard relations like b squared is equal to epsilon 1 of epsilon 2. And if you take the corresponding sum here, this again minus 1. Okay, so this is how we get two Virasoro algebras on the right side. In order to study what happens on the left side, if you want to study, it is a bit more difficult, and I am not going to prove anything here. I can say just in words that on the left side we have two factors. One of them is some rational and somehow small, SL2 level 1, and another is big. If I say k is large and complex, is most essential part. And it can be shown that actually what happens with the SL2 hat, the second factor, is like we apply Drinfeld-Sokolov reduction to it. So we again get Virasoro algebra with a parameter b squared is equal to 1 minus k plus 2. This is what just should happen to the parameter for Drinfeld-Sokolov reduction. This is, if you want, this is some sort of deformation argument. So you see, I take in my differential, I take diagonal L2. So this is E the sum. First E generated for the first algebra, for second algebra. If I okay, let me write here some sort of argument. Maybe I use some chalk. We have Q diagonal delta, which is the integral of E first and Z plus E second of Z minus 1 one can put here, introduce some parameter. Let me denote it. By epsilon here. On the generators of the first SL2. Is if epsilon is equal to 0, is epsilon equal to 1, this is just diagonal differential reduction with respect to diagonal SL2. If epsilon is equal to 0, this is differential reduction with respect to second factor. And then if we want to compute cohomology for epsilon 1, so what is the logic? We compute it for epsilon equals 0, and then look how they deform if we make epsilon alive. Study the corresponding spectral sequence. Okay. To make long story short, what we get? We get the Virasoro algebra. And for SL2 equal 1, so for this differential we have Virasoro algebra times SL2 equal 1, but the result in algebra, if I make epsilon alive, something changes, and the result in algebra I will denote by U, and this is called, at least in one paper, this is called Urod algebra. This is very good algebra. For my
What did you say? You said that initial. No, I mean, could you make a statement? It's like you got left hand side of the formula and don't have fraction side.
Okay, one of the formulas is this. If you agree on this notation plus with a completion, which means that some coupling, then this is a formula. Another formula could be like that you take the Urod algebra, you take its vacuum module, U0 say, multiply by vacuum module of this Virasoro algebra, L0 k plus 1. And this will be direct sum. No, sorry. Not for Virasoro algebra vacuum module with B minus 1 over k plus 2. I don't know, Rome, is it visible in this? And on the right side you will have direct sum over P1 to N B. So this summation looks very similar to what we have for the Virasora case, for the cassette case. In one factor is the same, and the first factor, what happens with the reduced model which we had for SL2 case after Dirichlet cycle of reduction. Maybe I can comment something about U, somehow complete it, say something more than just name. Let me put it as a remark. As a vertex algebra, U is isomorphic to affine SL2 of the level 1. So what we have if we take on the first term of the spectral sequence, if we do not put this term in the differential. And this is also the level 1 is if you want lattice vertex algebra for lattice I denote z square root of 2, so one-dimensional lattice with the length of the basic vector square root of 2. So something very simple. What does change under this construction is the stress energy tensor. T of U is equal to, okay, even before stress energy tensor, maybe I should say what does change is central charge. For SL2, the level 1 standard central charge is this is not, of course, central charge can be changed continuously by epsilon. Actually, even here there is a different, there are different stress energy tensors, and there are different central charge here. And central charge of U is equal to -5. And Tu of Z is equal, the formula is here is some number which I forgot, but this number should be such that the central charge is equal to -5. I forgot this number, sorry. And also what makes it odd that we also add here derivative of E of Z. And I think second. So we add in the Bosonization, this E of Z is some exponent, and we add to, so this is standard Miura or Feigen-Fuchs formula for the Virasora algebra in terms of bosonic field, and this is extension with exponents, which is quite natural.
What is
Phi is a field. If I consider this as a lattice vertex algebra, it means that I have Heisenberg algebra and take the sum of its Fock representations. And phi is a generating function of this Heisenberg algebra. So this is a sum of an z in power minus n over minus n, phi not equal to 0 plus a0 logarithm z, and plus also some operator which shifts 0 mode.
Sorry, dimension of the square of E is 3.
No, Of course, for normal people, yes, but today no. For rod, no. Because due to this shift of the stress energy tensor, dimension of EHZ becomes 0. A standard picture for SL2 head looks like this. We have highest weight vector, then we have fields of the dimension 1, E, H, and F, and so on. Some other fields. Here we have something like E2 prime of dimension 4, and so on. This is, how to say, this is a SL2 head for healthy person. And for rod, it is somehow transformed. So it's one part of his body becomes higher, and another part. So E of Z also have dimension 0. Instead of that, F of Z have conformal weight 2. This is 0. This is 2. Here we have E prime, and also have 2, and so on. So we have a bit, our parabola becomes somehow shifted.
Is it just a linear transform?
Yes, this is just, what happens, this is a gradient which so on this X, I have, probably in this direction, I have action of L0. You see what happens with L0. We have L0 of healthy person, and we add here H0 with some coefficient, which I forgot. So we just, this is just linear, and we have H0 on this direction, so just linear transform. This stays, this by 1, this by 2, and that's it. So this is for, this is for. This vertex algebra, what do you mean by just algebra? Associative algebra?
Yes.
No, you want to, I mean, for vertex
Because it's different.
so they differ. If you, of course, this equation of notations probably will correct me if I. So I mean, with vertex algebra mean that we have a structure of operator product. We have a operator state correspondence for each vector coincide field, and we know how to. And they satisfy certain properties, locality and so on. And if you add Virasora, there's some additional structure. This I use such notations, and this could be called, for example, chiral algebra. So they're the same as a vertex algebra, but different as a chiral algebra. What is opposite?
Chiral can be without Virasora. Vertex.
Which notation do you prefer?
Just grading. Same idea, but grading.
Yes. But,
So we have the same space of fields, if you want.
okay, but operator L minus 1 is the same.
Operator L-1 is the same. This second derivative do not have a term with the corresponding degree. It's the degree minus z minus 1. Okay. So this is a story about a shortcut of the story about a rod. probably, no, probably this is not the end. I just want to end one. Oh, maybe no, maybe. Okay, a little later. The central charges should be equal, or what? Minus 5 plus central charge of this should be equal to this sum of central charges. Does it contradict to some computation? No, this is the way how to find this minus 5. Okay. I like the story about the rod, but I mentioned it because I want to stress that the coupling we can couple, there are different objects which we can couple. So first I couple Virasoro and SL2. I can couple two Virasoro algebras in the case of some resonance. Probably instead of this, I, or maybe somebody else, can couple to SL2. So probably one can think, maybe I'll ask you is it true or not, that this construction is itself some Drinfeld-Sokolov reduction made on the second term for the Virasoro. So we have, one can think that we have two SL2 with the levels so here we have levels, okay, let me write them, K1 and K2, such that 1 over K1 plus 1 plus 1 over K2 plus 1. You see why I write this 1 over K1 plus 1 in my notation, no, not plus 1, of course, plus 2. In my notation, this is just a ratio of 2 epsilons. And in this case, I think this will equal to just 1. And consider this, consider extension. So again, I think the vacuum module will be direct sum of L to N K1 times L to N K2. But I don't know where the left side has good description. I think it is proven that the left side, that there exists such simple vertex algebra. No? In the paper which you sent me yesterday, there is a statement somewhere, maybe reference. Okay, maybe.
So which is the statement that this is vertex algebra?
Yes, this. Yes, localities. Yes, and the statements probably yes. This probably should be simple vertex algebra, so not direct sum of 2. This is not statement, this is state of art, I mean.
So you can be acquainted like with nice set construction.
So I don't know, and I asked everybody in the audience. So I don't know, maybe somebody. maybe can. But I think the general for this coupling, the general situation is there is no the fact that can be obtained by some other manner. This is some sort of exceptional isomorphism. It happens that sometimes the different constructions give you isomorphic objects, but this should be viewed as a surprise, if you want, as a something you should be happy. So, for example, the fact that in this part we get the Virasoro times some explicitly described factor is again a bit of a surprise, and this factor has its own Rod structure. Now I'm going to say, okay, so this is just what I wanted to say about the variation of the cassette construction, cassette example, which was yesterday. Now I want to say there is at least in terms of Virasoro, there is another quite natural direction of variation, is to play with this number. So, theoretically speaking, one can ask the following: take two Virasoro algebras with this certain parameters b1 and b2, and assume that b1 squared plus b2 squared, and ask whether they can be extended. And there are.
What's about what you said before? Was there some state? You got like right hand side.
Here.
Yes.
I think there is a statement, either proven or not, that this direct sum has a structure of the simple vertex algebra, and this vertex algebra is simple. This direct sum has a structure of the vertex algebra, and this vertex algebra is simple.
The sum is over integers, positive integers. Is that Virasoro?
No.
No?
This is L2 plus SL2. I do not by L any reducible model for any algebra.
But in this case, this again are fine.
Fine, this is the highest weight, this is the level. Can I?
Which is simple, it means what? It can be factorized.
Yes. Okay, I can, even without the word simple, that this sum has structure of the vertex algebra. This is, I have no doubt that this is true. There is no description of the left side. So probably it has. There is a left hand side, but we don't know. I don't know. I will be happy.
You want to say that this object just equals to itself, so it's not other algebras, which are isomorphic to that.
I don't say this. I don't know. This is somehow philosophical, maybe. Any object equal to itself, and if it is isomorphic to something, then this is isomorphic to itself. I don't know. What can I say? But the fact that this has structure of the vertex algebra. So we start with algebra, add certain representation, and the whole sum has a structure of the vertex algebra. Probably the word simple is also desirable in order to exclude some naive cases where we take multiplication by new fields by 0 or something like that. So in finite dimensional case, we take algebra, it takes certain representation of it. Sometimes it happens we can arrange all this into the algebra. Of course, there is a naive way to make this. Say that product of new elements is 0, and algebra acts on the representation as it acts. Okay, this is algebra, but not very interesting. But sometimes it happens that we can make
Does it have natural realization?
natural.
Realization. This is a vertical algebra state. Maybe you can describe it in other language.
And that's the question, how much is it equal to something another?
Yeah. No.
Don't know.
It is not known.
In general.
But what is the origin of this structure?
What we expect, for example, what we don't know is that if we take this and take Dirichlet-Sokolov reduction with respect to second factor, you get cassette algebra. You get the algebras which appeared in cassette isomorphism.
Can we say that this is like answer for no? This is like a homology of concept.
And they forget, if sum is 1, then it is asset to 1. What? I think so. Maybe
Theoretically speaking, I can make mistaken sign here.
it is for one choice of sign. If it is 1, it has other realization.
What is the counterpart of the statement for SL1?
Heisenberg, everything's usually quite naive. We have here we have Heisenberg plus Heisenberg equal to diagonal Heisenberg plus another Heisenberg, and there's no Dirichlet-Sokolov reduction. I would say the blow up bilinear relations of the Nekrasov function for Heisenberg are again naive, but still it's a relational function, still something. But here I don't think so. Let me move.
No, SL1, I think it is correct.
I don't understand. What do you mean by SL21?
SL21.
This? It has 4-dimensional bosonic part and 4-dimensional fermionic part. Yes, so I like 6 bosons. So this agrees with.
Anyway, I can say it, but it's not your subject.
No, it's not my subject. That's just for my education. Okay. I don't. Let's move further. As next, I want to say that in principle one can ask what happens with direct sum of two Virasoro algebras for other central charges. There is at least one example where we know something, where the sum is equal to -2. So in principle, expected that one can take any integer sum and get something. Maybe for some reason, maybe there are some restriction. For this I'm not completely sure, but -2 is definitely possible. So what should we expect? That we take direct sum of the Virasoro representation L1n before I wrote here 2n plus 1. And this sum has the structure of the vertex algebra. What does it mean geometrically? If I want to write this in terms of Nekrasov parameters, then it will this relation that sum is equal to -2 can be solved in the following manner. And geometrically, this corresponds to the resolution of C2 mod Z2, where resolution of the conifold singularity, where Z2 now Z2 acts on C2 by inversion sign of each coordinate. So this is this has some such geometric meaning. Now, what do we know about the answer? One. Okay, probably I cannot make it pedagogical, so probably I just write that actually the answer in this case also have some sort of factorized description, and this is a product of the F times NSR, where NSR is n equal 1 super Virasoro algebra. And F is just free fermion algebra. Free real fermion. So this is easy to write in super Virasoro, so I can write this the super Lie algebra with generators FR for R, for say half integer, and relations that supercommutator of FR and of S is equal to delta R plus S. Yes, you are right. NSR stands for Nevier-Schwarz-Ramon, who introduced it. This fermion can be seen in the following manner, that here I take the direct sum of representations of the form LP. So here in the vacuum module, I take the direct sum of representation of the form LP11 B1 times LP11 B2 plus LP13 B1 times LP13 B2 and so on. So here are odd numbers 1, 3 and so on. One can ask whether the even numbers. So what happens if I take LP12 B1 times the LP12 B2? And in principle, all this sum. So the sum of LP1 to n B1 times LP1 to n B2. And this sum will be in any case, the sum is expected to be a representation of this vertex algebra. In this case, it can be even included into the vertex algebra. So the highest vector of this of the first factor, so V12 times V12, has a conformal dimension equal to 1/2, and the corresponding field is just fermion. And I wanted, to be honest, I wanted to say during the first lecture today how to use this fermion in order to find coefficients Ln, which I mentioned, which were in the blow-up relation yesterday. I don't have much time, so again, when I come to something interesting which is related to Pinlevier, there's no time and no sound and everything. Oh, but just in words, I think I have 5 minutes till the break. So let me recall what is the meaning of these coefficients Ln. They appeared if we take a vector for the sum of the composite algebra of the left side and decompose the sum of tensor products of Whittaker vectors, having in mind the decomposition of this type. And here I have some coefficients Ln. Instead of n, I can write more explicitly. Here I have some a plus n b1 times a plus n b2. Let me write here, not n, b1 and b2. These indices correspond to the highest weight of the Verma module or Fock module of the left side when it is decomposed with respect to the Virasoro plus Virasoro on the right side. And the question how to find Ln, and what is it? There are actually, so there are several approaches. One of them is they can be defined from geometry if you interpret all this geometrically. And there is at least two approaches through conformal field theory. One of them is to find them use the screening operators, is to reduce this to some sort of resonance conditions where conformal blocks are computed using some integrals, and then somehow compute integrals, and then make analytic continuation. And another is to mimic standard approach to the 3-point function in conformal field theory. And with Anton we did this for this case and applied for Pinlevier, as usual. And the idea is the following. We can consider these numbers Ln could be viewed as some sort of 3-point function. We have certain field V1, then we have field, okay, let me write phi1, phi, this p plus let me state this in another manner. So in our theory, all fields are products of p1 times p2. And if we take 3-point conformal 3-point function, then again all fields will be which appeared here is a product phi p11 phi p2 let me write here not p a. I can denote this if you want by okay, you cannot denote it. And the ratio of these two factors, ln plus 1, is the ratio of these 3-point functions which are deferred by one intermediate field, B. If I take here B1, one of them is, in one of them we have B1 plus n, B1 and B2, then B2. And in the denominator we have B1 plus n plus 1, B1, B2. Let me write it. This is a picture. What? Say it again.
No, you've got the formula Ln over Ln plus 1.
Yes. Yes.
What is that?
There are these 3-point functions. The ratio of 3-point functions which are differs by in one field. I'm talking about we take a limit of conformal block. This is some sort of 4-point function that we have Verma module, then applying some vertex operator, then applying again some vertex operator. It doesn't matter. Forget about 4-point conformal block. I'm talking about we take a vector. This is what we have. Verma module, apply vertex operator, and take the image of the highest weight vector. Now now we have composite theory. So our initial Fermat module is actually sum of many modules. Where we apply, we also have a sum of modules. Our vector, from which we start, somehow comes to each of these summands. And we want to compare its normalization in point n and point n plus 1. And this normalization, if we forget about the whole symmetry and think about this as a Virasoro plus Virasoro, then we just have vertex operator from the n's tensor product and n plus 1 tensor product. And this formula means that we want to compare these normalizations. Okay. And just in words, I'm saying that this is done by how to do this. This is at least one of the approach that we just insert this 3-point conformal block. This 3-point function don't depend on the points due to conformal theory. One can think that everything here, this lives in 0, this lives in 1, or in my notation infinity, and third point lives in 1, for example. One can add this exceptional field, fermion, which lives in point z. And since this fermion, and this part is very simple with respect to this, fermion is a rational theory, and this fermion just lives on the left factor, we can look at the monodromy of this function with respect to z. And it doesn't have any monodromy. On the other hand, if we decompose this phi as a product of two phi-1,2 operators, then monodromy of this phi-1,2 is governed by a hypergeometric equation. And we have monodromy, and we have conditions that this monodromy actually cancels, since for fermion we don't have it. And this condition at the end of the day leads to formulas for Ln. Okay, what I'm going to say on the last lecture will not use this story about monodromies at all.